Okay, I'm going to do another demo of my tangible abstraction using red black tree as an example. So I'm just going to try to explain this pretty quickly and not worry too much about the context. Okay, so we're going to implement the red black tree insert method where you have a tree, red black tree T, and you have a value V and you want to insert it. You start off with just the tree, and then you use binary insert to insert v into the tree, which yields a node n, and that node is colored red, right? So here we have a picture of what the tree looks like after the binary insert occurs. We have the top part. These triangles represent red-black trees, subtrees. This is the top part. This is the part above n, and these are the parts below n. So these are just black-rooted, one black length trees, which are empty because the black root means that the first node has to be black, and the black height of 1 means that they can only have the nil pointer inside them. Okay, so and then we have our node n, which is red, and then this says basically that n sibling, if it exists, has a black height of 1. Right? And black height is what you need to worry about when you're trying to create a proper red-black tree. So here, if this n has to have the same black height as its sibling 1, and it has the black height of 1 because red doesn't contribute to the black height. These subtrees are all 1, but this red node is a problem because we don't know what the parent of n is because it's abstracted behind this compressed red-black subtree. And if we turn it black, then it becomes 2, and we can no longer compress it. So we have to sort of do something about this parent. But first, we're going to generalize this picture a bit. We're going to, instead of saying, instead of looking at these trees where all these values are 1, we're going to make them all k, because we're going to have to use it in a loop later on. Right, so here we can just think of k as a stand-in for 1. Okay? So now we've started this. Now the first thing we need to do is take apart its parent. Right, so this tree has to be decompressed. So we decompress it. We get this p of some nondescript color here, which we're also going to expand. And so what I'm doing is I'm pressing down. Let's do that again. What I'm doing is I'm clicking on the compressed subtree, and then I'm saying, well, what options do I have? Well, there's one option at the bottom, which is to expand. Right, I do that, and it expands, and it's adding code on the left as that's happening. So I do the expansion here, and then I'm going to expand again to get rid of, to make p either red or black. Okay, so the first case that we get to, so we have 3 cases. We have the parent of n is black, we have the parent of n is red, and because a red node has to have a black parent, we also have a grandparent that's black, and then we have the parent of n is empty. Right, so if it's black, right, this is already a well-formed red-black tree, so we can just compress that and return. Okay, and if it's empty, well, it's not yet a well-formed red-black tree, but all we have to do is toggle the color of n from red to black. And so we do that by clicking on the color dot, which turns the color to black, and then we can just compress and return. So the only case we have to worry about is where n's parent is red. Okay, so this is a little bit more complicated, but we're going to look at the grandparent, the uncle of p, I guess is what they call it, right? So we're going to expand that out a little bit. So right now we don't know if this subtree has a black parent, a black root or not. And when we do this, right, we get 2 choices where, the subtree has a black root, or it has a red root, which is a red node root. And so we're going to deal with this one first, right? If it has a black root, then, well, we want to rotate p up and make this a different shape. But now I've been ignoring this one for the previous part of my talk, right? But the orientation of, whether p is the left child of g or the right child has been abstracted by this wildcard. It basically says that, this axis could be flipped, right? So p could actually not be the left child. It could actually be the right child. And the same goes with n. It could be the left child or the right child of p. because this wildcard says that either case is fine. But now we need to actually know whether they're the left or right children. But actually, we don't really need to know that. We just need to know if they're the same, if this is a left left or a right right. Okay. Otherwise, then we can do our rotation. So I'm going to click the wildcard under the G node, and I'm going to drag it to the P node, and basically it says they're equal, right? This is basically doing another switch statement, which is comparing the axes of left and right. And if they're the same, it's like this, and if they're flipped, then, well, basically if they're flipped, then we just say, well, we can keep this the same, and then we just flip the left and right children around, and then they're the same again, right? So let's look at the case where they're the same first. So all we have to do is rotate P up. So I'm going to click on P and then do the rotation. Okay, now we have our tree, and all we have to do is make this black and make this red. And now this is a proper compressible tree. So we just compress it and return. Now for this one, right, if you look at this, right, we have this picture and this picture. Well, if we can get the node up, right, this picture looks a lot like this picture, right? So we can just do a go-to there. So this little blue box pops up saying that there's go-to possibilities here, but we could go to here, or we could go here, or we could go here, and then we can continue the program, and we're just going to go here, which is the same. Actually, all this would functionally be equivalent, but this is less computation because we don't have to repeat work. Right, so I've done that, and it does the go-to, and we're going to go to L0. So we do run rotate, and then we do another rotate. And if you look at the Wikipedia article for red black tree insert, it's basically they basically do the same thing. Right, and now in this case, right, we have a red uncle. We looked back up here, right? We had either the black uncle or the red uncle, and if we have a red uncle, right, we have to do some recursion. We can color these things black and color this red, and then we compress these two trees to be the k+1. And if you look at this, it looks a lot like what we had at the beginning, and that's why we had to generalize all the 1s to k, because we're going to have to, we have to loop back up at this point. So we're going to click our go-to square and attach it to up here. Now, when we get to this point, right, we'll go back up here, and then some of the variables will be adjusted. K is going to be 1 greater, which means we work our way up the tree, and G will be the G node. The G node from our base will be replaced by, becomes the new N. Okay, and that's it. This is a working, pretty correct insert for a red black tree. Thank you.